Good afternoon to all. Hope screen is visible to everyone. Am I audible?
Yes, sir.
So hope screen is visible to all.
Yes, sir.
In the previous class, we had a discussion about the instruction set computing with respect to embedded system. Obviously, not only in embedded system, in all computing systems, how the instructions will be executed. Okay, which environment is there. So that those are nothing is reduced instruction set computing and complex instruction set computing. So those two environments are introduced, and we had a discussion about the differences between. After that, the architecture, how the internal block diagram or the internal structure, we may say the architecture of that embedded system. Not only embedded system, in all computing system we have the hardware and Venom, or we may say another name of that Venom is Princeton architecture. And we move towards the memory, how the memory, the data storage in the memory. The concept is going to be having two types or two formats. One is called as Big Endian, another one is called Little Endian. So what are the Endians? So these Endians specify the order in which the data is stored in the memory by processor operations in a multi-byte system. Obviously, here the data what we are going to store or retrieve. So these two formats are dedicated to storing the data in the memory, Big Endian and Little Endian formats. So NDNS specifies the order in which the data is stored in the memory by processor operations in a multi-byte system. Obviously, the system is designed for bytes. Okay, the data stored in a byte, so it may be single byte or multiple bytes. So I hope you got the definition of this NDN, how the data is stored. So what this data can be stored in a memory in two different ways. What are those two ways? The first one is Little Endian and another one is Big Endian. So what about this Little Endian concept of storing the data in the memory? Higher order of data byte at the higher memory and lower order of data byte at locations just below the higher memory. So it means that in the Little Endian format, we have multi-byte nothing but we may have more than one byte. So suppose if you go for more than one byte, obviously we need to categorize those bytes into higher end byte and lower end byte. So suppose if you have a 2-byte data, 2-byte data. So in the 2-byte data, the first byte is obviously from LSB to MSB bits, MSB to LSB or LSB to MSB. So the MSB byte, the most significant byte, is called as higher end, and lowest significant bit is called as the lower end data. So here the lower byte is stored in lower memories and higher byte stored in higher memories. So such format is known as Little Endian. What about this Big Endian? It is reverse of this Little Endian. Means the lower order of data byte at the higher memory and higher order of data byte at location just below the higher memory. So just below the higher memory, but below higher memory, obviously we are going to find lower memories, memory locations. So what this Big Endian is going to provide, this facility, this format is going to provide the storage of lower byte in the higher memory locations, and higher byte data is stored in lower memory locations. So this concept will be clarified having these diagrams. Obviously, you can observe if I go for the memory structure, the data memory structure in the memory. Suppose obviously we begin with the base address. So here we are going to observe the base address. This one is the base address. Let me say the label is the 20,000. Okay, in hexa value it is 20,000. So obviously here the memory locations are going to begin from. So whatever the base address, so the base address is considered as lower memory. So above that one, above that base address are going to be considered as the higher end memories. So here it is 20,000 memory address is the lower memory location. Then the next one is 2001, 20,001. It is the next memory location. 20,002, 20,003. So from base address above plus 1 plus 2 plus 3 and so on. So now considered higher end memory. So here the lower memory, higher memory. Obviously you may say whatever I have discussed, it is how the movement is, it is from lower memory to higher memory. So this example is illustrating data of 4 bytes. Data of 4 bytes. So here first byte is byte 0, second byte is byte 1, then byte 2, then byte 3. So here the Little Endian, what this format is, here the lower byte. So if you go for 4 byte data, the from LSP nothing but byte 0 and byte 1. Byte 0 and byte 1 are considered as lower data. Byte 2 and byte 3 are considered as higher byte data. So lower byte data are stored in the lower memory locations. Means byte 0 and byte 1 are stored in lower memory, and byte 2 and byte 3 are stored in higher memory. What about in Big Endian? It is just a reverse. Means higher order data. Higher order nothing but byte 2 and byte 3 are stored in where? In lower memory locations. So what are the lower memory locations? It is base address and base address plus 1. Then what about lower byte data? Lower byte data, that is nothing but byte 0 and byte 1. They are stored in higher memory locations. What are the higher memory locations? They are base address plus 2 and base address plus 3. So this one is the format used in the process of storing the data in memory. So storing the data in the memory is called as Endian process, and we have two types. One is Little Endian and Big Endian. Okay. So anyone is going to reply if the data size is of 6 bytes. Suppose the data size is of 6 bytes. So how you are going to allocate the memories for Little Endian? Little Endian. Anyone can reply. If the data size is of 6 bytes, then how we are going to allocate the data in the Little Endian format? So may I ask Chetan? Okay, let me ask Yuvraj Swami. So Yuvraj Swami,
Sir.
how you are going to allocate the data in the memory, how you are going to store the data in the memory with respect to Little Endian if the data size is of 6 bytes. Got this concept? Big Endian and Little Endian formats. Yuvraj Swami?
Yes, sir.
Okay. So how the 4-byte data is stored in the Little Endian format? This is not Viva question, Yuvraj Swami. You are not attending any Viva question. Practical lab. Yuvraj Swami.
Sir.
4-byte data, how it is stored in Little Endian.
Higher memory.
Okay, let me explain you once again so that you can answer for my question. So let me go for once again this Little Endian and Big Endian format data storage. Okay, memory. There are two things because we have the memory locations beginning from base address to higher end memory location. So base address is the lower memory location. Okay. Then if I go for by seeing this diagram, you can have the clear idea about how the Endian concept is performed. So here the base address is 20,000, nothing but the first memory location. First, second, third, fourth, and so on. So instead of giving the numbers, we are going to name them as lower memory and higher memory. So higher memory are nothing but above the base address. Okay. So base address comes at lower memory location. So here the lower memory, the memory is moving from lower to higher. So if I suppose the 4-byte data is there, if I allocate the 4 bytes in this fashion. So byte 0 at lower memory, byte 1 next higher end memory, byte 2 next higher end memory, byte 3 above that higher memory of byte 2. Okay. So byte 0 and byte 1 are in the lower memories, byte 2 and byte 3 are in higher memories. So what about here? Means lower first, upper next. In the Little Endian, lower first, upper next. What about here? In the Big Endian, higher first, lower next. Okay, so the first byte allocated in the first memory, or you may say lower memory, it is higher byte, that is byte 3. Then the next lower byte is byte 2, which is stored in next higher memory. Byte 1 is lower byte of byte 2, it is stored in higher memory, that of byte 2. Then byte 0, it is just above the higher memory of byte 1 location. So let me simplify once again. In the Little Endian, so lower byte first, higher byte next with respect to the memory location. What about Big Endian? Higher byte first, then lower byte. Okay. Now, by having this concept, Yuvraj Swami, you just explain if I have a 6-byte data, so how you are going to allocate the data in the Little Endian format.
Giving base address plus 4 plus 5 and plus 6, sir.
Okay, these are the memory locations you have in the memory. So how the data will be stored in those memories?
And byte 0, byte 1 and byte 2 are lower memory, and byte 3, byte 4 and byte 6 are higher memory.
Okay. Byte 6 is there. Byte 6 is there.
Up to byte 6.
No, no need to unmute yourself. Okay. No need to mute yourself. Keep it unmute. When I say unmute, you just unmute. Okay.
Okay, sir.
So now unmute. Then talk. So what is the number? What are the labels you are providing for bytes? So which one is the last byte?
Byte 3, sir.
No. Total.
Byte,
If you have 6
byte
bytes,
6. Byte 6, sir.
so what was the last byte label?
Base address plus 4. 0 into
Byte.
2.
No, first give me the bytes. How you are going to divide the bytes?
Byte 0, 1, 2, 1 and 2 are lower byte, and 3, 4, 5, 6 are higher byte.
3, 4, 5,
Higher
6.
memory.
So how many bytes are there? 3, 4, 5, 6 means
3, sir.
3 now.
6, 6.
See,
6 byte.
byte. So 6 bytes means what are the labels I am asking? You are beginning from byte 0. Which
Yes,
is
sir.
the last byte?
20,005.
No, I
0
am not
into
asking the memory. I am not asking the memory. I am asking the which byte number will appear. Which byte name or label? Byte 6 or byte 5?
byte 5. Sir.
Byte 6 is there or not?
Don't know.
The bird will kayak.
Yes,
You
sir.
just have the finger. So allocate 6 bytes. What is the first finger name? First byte name, byte 0.
Byte 0.
Next finger,
Byte 1. Byte 2.
next finger. Up to 6 fingers. What's the last finger
Byte,
name?
byte 5, sir. Byte 5.
Then byte 6 is there or not?
No, sir.
No. So now tell me how you are going to allocate each byte in the memory location.
Byte 0, 1, 2.
Okay,
Byte
those are
0,
in lower memory.
1. Lower memory.
Then remaining 3 are there in the higher memory. What are those remaining 3?
Byte 2, byte 3, and byte 4. No, byte 3, byte 4, byte 5, sir.
Byte 5. So byte 6 is not there, isn't it?
Yes. Yes, sir.
Okay, fine. Next it is RT. RT. Can you explain how you are going to store these 7-byte data in the big Indian concept? 7-byte data. RT 400, EC 400. Unmute and you can reply. 7-byte data, how you are going to store in big Indian concept. Because these things are important in the lab, because you need to play with the memory locations. Okay, you need to store the data in the memory, read the data from the memory, how you need to add the address, base address. I need to add +3, +4, or +6, or whatever the memory, different concepts in the lab. So you must be thorough in these concepts. So in the big Endian RT, how you are going to allocate 7-byte data. Because next concept is memory only, what I need to explain to you. Let me unmute yourself.
Yes, sir.
Okay, head. ಇನ್ನು ಎನ್ವೈರನ್ಮೆಂಟ್ ಕ್ರಿಯೇಟ್ ಮಾಡ್ಕೊಂಡಿಲ್ಲ ನೀವು, ಹಾಲಲ್ಲಿ ಕೂತ್ಕೊಂಡಿದ್ದೀರಾ. Arti, why you are muting yourself? Unmute yourself. Keep the mic open. Okay, no. In the big Endian, how you are going to allocate the memory of 7 bytes? No audio from your end. Sorry, your mic is not good. Whatever device you are using, it is not at all good. Maybe your mic is good, but mic is not good. Okay, let me go for Meghna, EC018. Meghna.
Yes, sir.
Okay, now reply for the same question.
0 to 6, sir.
Too much disturbance. I can't hear you. Mic issues. I don't know how you are understanding my class online, not only my class, all the classes with such equipments. Those are part of the embedded system. Keep it in mind. The mic, whatever the previous class I had given the example, the mic and earphone, mobile phone, internet data communication, that is internet, Wi-Fi, SIM card, all those are part of this embedded system. If one is not going to work, means one part is not going to work, we say that embedded system is a failed system. And we won't use that embedded system. So the purpose of this embedded system is to meet all the requirements. That is data communication, data capturing, data representing, data usage, communication, interfaces, like whatever the mic or headset you are using, you are connecting to that embedded system externally. It has to support. If it is not supporting, means either the headset is not giving proper performance or the mobile phone interface port. So Meghana, I need answer. ಸೊ ನಿಮ್ಗೆ ಕ್ಲಾಸ್ ತಗೋಬೇಕಂತ ಹೇಳ್ಬಿಟ್ಟು ನಾವ್ ಹೆಂಗ್ ರೆಡಿ ಆಗ್ತೀವ್ರಿ, ನೀವು ರೆಡಿ ಆಗ್ಬೇಕಾಗತ್ತೆ. ಇಟ್ ಇಸ್ ನಾಟ್ ಲೈಕ್ ದಟ್ ಯು ಆರ್ ಸಿಂಪ್ಲಿ ಆನ್ ಅಂಡ್ ಕೀಪಿಂಗ್ ದಿ ಸ್ಕ್ರೀನ್ ಆನ್, ಆರ್ ಯು ಜಸ್ಟ್ ಲಾಗ್ಡ್ ಇನ್ and you are doing your work. It is both input and output. If input is proper, output must be proper. Embedded systems are going to receive input and they are going to alter the behavior of outputs. So in this online classroom embedded system, I am at input side and you are at output side. As I am giving the input, output must be changed, not simply defining the output ports. So your all are output ports. I am the only input port. So I am input is there. So according to embedded system, output must be altered, modified, changed. Spurti, EC039. Unmute and
Yes, sir.
unmute and give me the answer for this big Indian example of 7 bytes.
We have to take from 765432110.
Okay, 7. You begin with the byte 7, huh?
Yes, sir.
I told 7 bytes. If you say
Then we
byte,
have to start from 6543210.
once again repeat.
From 6543210, sir.
So how you are going to allocate these memories from top to bottom or bottom to top?
From top to bottom, sir.
Top to bottom you are going to allocate the memory locations.
Higher one we have to keep at us.
So top, let me tell you these words. Top means higher memory location. Bottom means lower memory location. Don't go for the image, what it is displayed on the screen. So image is there, and what is the address? Base address. On the top it is base address, nothing but the lower memory location. So don't tell that from top to bottom. With respect to image, I'm not. You should not give the answer with respect to image. With respect to memory locations, you need to give the answer from lower to higher or higher to lower. Purti, you are going to allocate byte 6 to byte 0 from lower to higher or higher to lower?
From higher to lower.
Higher to lower. Sorry, it is not higher to lower. I think let me repeat you once again. The Little Endian concept is storing the data from lower memory location to higher memory locations. The lower data in lower memory, higher data in higher memory. Big Indian is reverse of that one. That is nothing but lower data, it is in higher memory, and higher data in lower memory. Now tell me in Big Indian, the 7 byte data means from lower data is byte 0 and higher data is byte 6. So byte 0 to byte 6 are from lower data to higher data. So how you are going to use the memory to store the data? It is from higher data, that is nothing but byte 6 to byte 0 are stored in lower memory to higher memory. Don't go for the image. ಒಕ್ಕರೆ ಇಮೇಜ್ ನ ಉಲ್ಟಾ ಹಾಕ್ಬೇಕು ನಿಮ್ ಪ್ರಕಾರ ಹೇಳಿದ್ರೆ ಹೌದ್ ತಾನೆ ಇಮೇಜ್ ನ ಉಲ್ಟಾ ಹಾಕ್ಬೇಕಂತ ನಿಮ್ಮ ಅಭಿಪ್ರಾಯ. ಸೊ ಬೈಟ್ 0 ಅಂದ್ರೆ ಸರ್ ಬಾಟಮ್ ಇಂದ ಚಲೋ ಮಾಡ್ರಿ ಲಾಸ್ಟ್ ಯಾಕೆ ನಾ ಇಮೇಜ್ ಹೆಂಗಾದ್ರೆ ಹಾಕ್ಬೋದಲ್ಲ. ಐ ಮೇ ಪುಟ್ ಇನ್ ವರ್ಟಿಕಲ್ ಫ್ಯಾಷನ್ ಆರ್ ಐ ಮೇ ಪುಟ್ ಇನ್ ಹಾರಿಜಾಂಟಲ್ ಫ್ಯಾಷನ್. Don't go for the diagram. If you go for the diagram, what are the addresses, labels are provided in that diagram. You just understand the concept. Okay, fine. So you can mute yourself. So this is about Big Endian and Little Endian format. So simple format. So don't get confused, because if I go for previous slides, you may get too much confusions because it is purely theory part. Okay, the risk and CISC purposes. Whatever, if you read one or more than one, so obviously you're going to get confusion. So in the concept. Next comes it is, as I told, in the next slide, I am going to begin with the the memory itself. So here the memory we are going to discuss is about the types of ROM and RAM. Read-only memory, random access memory. So what this memory is? Memory is an important part of a processor or a controller based embedded systems. Obviously, it is the element of that embedded system. So some of the processors or controllers contain built-in memory, and this memory is referred as on-chip memory. What this on-chip memory concept is? If the memory is inbuilt in the embedded system is known as on-chip memory. Others do not contain any inside chip and requires external memory to be connected with the controller or the processor to store the control algorithm, or you may say the data. So it is called as off-chip memory. So we have memories will be on-chip, which are inbuilt within the processor. Off-chip, nothing but they are outside or external memory are connected to the chip. Now, go for, we got what is this memory. So memory is the important part of this embedded system for storing the data or storing the code or programs. So on-chip memory and off-chip memory. So go for the type of this memory. It is ROM, program storage memory. Program storage memory, or the code memory, or read-only memory. We can have different labels for this ROM. Program storage memory, where you can store the programs. Code memory, where you can store, means both are same, program and code. Then read-only memory, so where you are going to use this read-only memory. Obviously, the algorithm, which will be secured and read purpose. So ROM, it is the varieties of ROMs what we are going to have in an embedded system. So we have the code memory, which will be in the form of NVRAM, flash, ROM, masked ROM, EEPROM, and EEPROM. So these are the varieties of this ROM. Let us discuss one by one. Let us have this. What is this code memory, or you may say the concept of this ROM? The program memory or code storage memory of an embedded system stores the program instructions. The code memory retains its contents even after the power to it is turned off. Means what? It is a permanent memory. Whatever the data it is going to be stored, it is only read purpose, not for write purpose. You can only read, and after the power, if the power of the embedded system is turned off, then too the data whatever there in the ROM, it is safe and it is stored permanently. It is such environment that concept is called as non-volatile storage memory. Non-volatile storage memory means the data or the instruction or the program, whatever it is written, it will be permanent and it is read only. So it is non-volatile storage memory. So types of this ROM, one of the example is masked ROM or MROM. Is a one-time programmable device. Obviously, once I say it is program memory, which is a permanent storage location, and it is going to maintain the data as it is, even if the system is in the off mode, and it is known as non-volatile. So how you are going to write the programs? When you are going to write the programs? When you are going to read the programs? How you are going to read those programs? How you are going to use that memory? When you are going to write and how you are going to read? So based on that varieties, functions done by the user end. So we have varieties of memory of ROM. One of the example is masked ROM. So is a one-time programmable device. Means this ROM is programmed only one time. Then the device is factory programmed by masking at the time of product itself. Means this is purely created in the industry as per the requirement of end user. So according to the data provided by the end user, this ROM is designed by the industry itself. It is a factory created ROM. Okay, so the data, whatever the program, this chip, this memory chip is written, and the data in that one, it is purely stored from the industry itself. End user can't write anything in this ROM. End user can't write in this ROM. So masked ROM is a good candidate for storing the embedded firmware for low cost embedded devices. So this MROM is used for the low cost embedded devices. For example, if you go for a toy which is going to play a musical audio, so it is of cost, let me say 30 to 50 rupees. In the market you are going to find, obviously it is a China product what we are going to use. So in that audio device, okay, if you go for that toy of mobile phone, let me say for children, so that is going to, each button is going to play different songs. Okay, so that song, it is pre-built in that ROM, and that program, that song is nothing but the code. That code is designed by the industry itself, factory itself. The end user can't change any program, any song, or can't program that device. So one of that one, that ROM, the memory. So when the child is going to press button number 1 in that toy, a song will be played. For button number 2, different song will be played. Button number 3, different song will be played. So here, each button is allocated for a song available in the memory, and that data, that memory is predefined, inbuilt by the factory itself. Another one is ROM, or one-time programmable memory. ROM, programmable read-only memory. So the difference in MROM and PROM is small difference. In the MROM, the program is written by the factory only one time. What about in PROM? The user can write the program only one time. Hope you are getting this programmable read-only memory. Unlike masked ROM, the one-time programmable memory, sometimes it is called as OTP, or programmable read-only memory, PROM, is not pre-programmed by the manufacturer. Industry is not going to write the programs in that chip, in that memory. It is going to give blank chip, empty chip to the user. So there is a facility for end user is responsible for programming this device. We can write one program only one time. Once again, it is not reprogrammed after programming. So this is the difference between MROM and PROM. Means what? If I give the same toy, musical toy, to the end user, so the musical toy from the manufacturer, it is coming empty. It is coming empty. So that industry, that manufacturer is giving the permission to, you can put any song to any button. Empty memory will be given in that toy. So what end user is going to do, that child is going to do, he is going to allocate one song for button number 1, another song for button number 2, third song for button number 3, and so on. So once it is programmed, we are going to call that putting the song in, dedicating or storing the song in the memory for respective buttons. It is called as programming. So once it is programmed, once again, after programming, it can't be reprogrammed by that end user. So this is the PROM. Then EPROM, erasable, programmable. So it gives a flexibility to reprogram the same chip. So EEPROM stores the bit information. To reprogram, it needs to be taken out of the circuit board. So what this EEPROM is going to give? Obviously, the flexibility is given for reprogramming. So master ROM, no reprogramming. PROM, no reprogramming. What about this EEPROM? It is programmed, reprogrammed. But here, based on the facility, how it will be reprogrammed, it is not on board. So if device is there, if you are using EEPROM, so and if you want to alter the contents, if you want to reprogram it, means you need to remove this memory from that device, okay, and connect it to erasable environment, okay, and it is going to take 20 to 30 minutes for reprogramming. So it is a tedious and time consuming process. So it is going to take 20 to 30 minutes to reprogram. The reprogramming concept is how you can't, okay, in that toy, if you want to change, once again, let me go for the toy itself. So in that toy, after PROM, means you have, the child has inserted some programs for each button. Once again, the modification will be done by the child, that child. So the EEPROM will be used for modification. So how the program will be done, reprogram will be done, not directly connecting that device, that toy to any reprogramming environment. So the memory will be removed from that toy, then it will be given to the reprogramming environment. That is ultraviolet erasing devices will be used for this EEPROM reprogramming. Obviously, it is going to take that tedious one and time consuming. Then comes it is EEPROM. What is this EEPROM? Electrically erasable, programmable, read-only memory. EEPROM. Nothing but here the difference is EEPROM you can reprogram within the device, within the embedded system. No need to bring that one. Okay, you need to uncircuit that one and go for reprogramming, and once again connect that device to the board. That is available in the EEPROM. What about electrically erasable programmable read-only memory? Here the concept is same. You can reprogram this memory within the device itself. No need to remove it and rejoin it. Next comes it is flash memory. The flash memory, obviously, it is the known concept in nowadays. It is the latest read-only memory technology. Here, what we are going to observe it is flash, nothing but your SD card or pen drive. Those are the example of this flash memory, which are connected to device externally. The flash memory is the latest ROM technology and is the most popular ROM technology used in nowadays. So flash memory is organized as sectors or blocks or pages. So here, each sector or a page should be erased before reprogramming. So whatever the flash memory it is, read-only memory. We can write it. Means it is a non-volatile. Even if you remove that pen drive, the data, whatever there in the pen drive, it is kept as it is. There is no loss of data. Even there is no power to it. Okay. So that is flash memory. Then comes it is NVRAM. So this is a special type of memory which comes in both types, volatile and non-volatile. Volatile and non-volatile. It comes in both the categories. It is a example of RAM also. It is example of ROM also. Read-only memory, random access memory. It is example of these two, NVRAM, non-volatile RAM. Means it is the random access memory which uses a battery backup. Means what? Here it is a RAM. Actually, it is going to act as a RAM for temporary usage. Store the data temporarily and remove the data temporarily. And that is RAM. It is with battery backup. Means if you make the system off, this extra supporting battery is going to provide the power supply to the separate memory, so that whatever the data available in that memory, it should not be erased. So it is a battery backup memory, non-volatile RAM. Okay, so a minute battery for providing supply to this memory in the absence of external power supply. So these are the types of ROM, read-only memories. So we have what is this code memory, where we can store the data, store the instructions for read-only purpose. Even though the power is off, the data will be kept as it is securely. Then the types are based on the how the program will be done, how the read-only environment will be there. It is masked ROM, PROM, EPROM, EEPROM, flash memory, and NVRAM. Next, if you go for the next memory type, it is RAM, a volatile memory. RAM is the memory or working memory of the controller or a processor. Controller or a processor can read from it and write to it. RAM is volatile, meaning when the power is turned off, all the contents are destroyed, removed, erased. Means it is not going to be used for storing the data for longer period. Whatever the data is stored, it is up to the system is on. When the system is off, obviously all the data will be erased, so that we can use this one for reading and writing purpose while the system is on time. Then it has three types of RAMs. One is a static RAM, stores data in the form of voltage. They are made up of flip-flops. Static RAM is the fastest form of RAM available. So we have SRAM, DRAM, and as I told, NVRAM. So NVRAM, non-volatile RAM, it is the example of both RAM and ROM. So static RAM, it is the most using memory, RAM memory in the embedded systems. And it is in the form of how the data will be stored. It is in the form of voltages, and it is going to be designed by using flip-flops. So you can observe this diagram, how the read and write processes are done with SRAM. So this implementation, the SRAM, it is simpler form, and it can be visualized how it look like. It has two cross-coupled inverters. Two cross-coupled inverters. Obviously, what is the inverter? The output is inverted value of input. Okay, output of this inverter is inverted value of input. If input is 0, output is 1. If input is 1, output will be 0 from these devices, with read and write control through transistors. Obviously, we know these FETs. These FETs are used to have the connection with the lines. When the transistor is on, the line is connected. When transistor is off, line is disconnected. So whenever if you want to, this one is the memory. It is the simple memory with write control and read control. So write control is going to use data to be written, and read control is connected to the data to be read. Okay, so how this memory will be performing read and write processes. So you can have this one, this diagram. If you carefully observe this diagram, let me remove all these things. Okay, so here, whenever if you want to perform write control, and this memory, whatever the data you want to store, it must be inverted value. It must be inverted value. If you want to store one, you need to data to be written, it must be inverted value, that is 0. If you want to store 0 in the flip-flop, the input what you need to provide, the data what you need to provide, it must be inverted value of that one, that is 1. That is 1. So how it is? What the data what we are going to provide, the data storage is just inverted value of that. Inverted value of that. So if you want to store 0, you need to supply 1. If you want to store 1, you need to supply 0. Okay, so go for this one. How the things will be there. Let me remove. Go for one example. So if you want to write data, so to write data, the write control signal must be 1. It must be high voltage. What about read data control? It must be 0. It means this is the transistor just connecting this flip-flop to the respective line, read line or write line. So if you want to write the data, to write data to this flip-flop, this inverted cross-connected inverters, you need to supply what? Write control must be high state. Once the input for this transistor is high, obviously this transistor is connecting the overall flip-flop to this data write line. So if you want to store logic 1 in this memory, what you need to do? I need to supply 0 here. If I supply 0, what is the input to this? Let me say inverter 1 and inverter 2. Inverter 1 and inverter 2. So what inverter 1 is receiving as the input? It is 0 because 0 I am supplying in the right line. So if it is 0, what is the output from this inverter 1? It is the logic 1. So the same logic 1 is going to act as what? Input to this inverter 2. So what is the output from the output from inverter 2? It is once again 0. So in the data read line, what data is available? 1. What data is available? 1. Means this flip-flop is storing which value? 1. The flip-flop is storing, the memory is storing value 1. How? By supplying 0 data in the data write by making this write signal control 1. This is writing the data. So as I said, is the data read line is having any value? No, because the read control is in the off state. This is switch, this transistor is acting as switch. This switch is off. This switch is off. So whatever the data in the memory, it is can't read by this data read line. Now go for this data reading purpose. So the data reading purpose will be there. If you want to read the data, make this write control off, and the read control on. So once you make this write control off, this transistor will be off, means no data will be supplied to this flip-flop. Once you make this read control on, this transistor, which is at the data read side, it is going to be on, and this one is on, it is act as a closed circuit. Means whatever the data in the flip-flop, everything is flowing at the data read line. So what is the data is read? It is read, the value is 1. So what is the value stored in the memory? Value 1. And what is the data read? It is value 1. Okay, this process is there in the static RAM with the help of 2 cross-connected coupled inverters with read and write lines and control lines. And control lines are connected to transistors to make that the read and write task easy by making the respective switch on and off. And SRAM are low capacity and high cost. So capacity of this one is only 1 bit, 0 or 1, and the cost, obviously, if you want to go for more memory, the size of the memory is a gigabyte or megabyte or terabyte, how many flip-flops you need to use, how many transistors you need to use. For storing the data 1, you have this architecture. For storing multiple data, obviously it is a more number of equipment components are used to design that static RAM. Obviously it is a high cost. If you go for dynamic RAM, it stores data in the form of charge, not voltage, in the form of charges. They are made up of MOS transistors, metal oxide feed effect transistors, and the advantage of this dynamic RAM are its high density and low cost compared to static RAM. The disadvantage is that since the information is stored as charge, so the data is stored in the form of charges, not as voltage. So voltage, until unless the power is there, voltage is there in that SRAM. What about DRAM? It is going to store the data in the form of charges. Even though power is there, the charge, whether it is held or not, charge is available there or not, in that respective memory, the data will be available. Until unless charge is there, memory is storing the data. No charge, obviously data is lost. So our charge, it gets leaked off because of these components. Obviously, we are going to find the leakage of charges because of the whatever the component we are going to use to store the charge. Even though in our mobile phone also, even though when the mobile phone is not in working, we are going to observe there is a reduction in the charge. It is due because of leakages. To prevent this, they need to be refreshed periodically. So what we need to do, we need to refresh that memory. Not only we just kept that, we store that data in the memory, and the data will be safe until unless the power is on. It is not like that. Even though power is on, we need to go for periodically refreshing that memory because of that structure. So you can observe that structure like this. So DRAM, it is going to use simple one MOSFET with one capacitor. So whatever the data you want to write, so the DMOS on the drain side, whatever the data you want to store, that will be available, and what data you want to store, that will be kept in the form of charges in the capacitor. So this capacitor is used to store the data in the form of charges. Okay. So what you want to write or read. So it is based on the word line. So if you want to make this transistor on, so when the transistor on, if the data bit is 0, what is going to happen? Whatever the capacitor is going to discharge, it is going to discharge. So what is the data in this memory, in this capacitor? It is 0 because no charge is there. Means no charge. It indicates bit 0. So bit 1. If the data line, it is 1, and if you make this transistor on, this one is going to be stored in this capacitor in the form of charges. Means what? It is going to charge. It is going to charge when the bit line is 1 and transistor is on. So the data stored is 1. Okay. So when the transistor is on, whatever the bit data is there, if it is 0, capacitor is going to discharge. If bit is 1, capacitor is going to discharge. The state of charge and discharge are considered as logic 1, logic 0. Data 1, data 0. So as the name indicates, it is in the form of charges. If capacitor charged, bit 1 is there. If capacitor is discharged, bit 0 is there in the memory. Then the last one is NVRAM. As I discussed in the previous ROM concept, this NVRAM is what? It is a read-only memory, and it is going to use, as it is the part of this RAM, means if the power is going to be off, all the data must be removed. So it should not be removed. It should be stored permanently. So it is going to use extra battery. Okay, it is with battery backup, so that even the power of the memory is going to keep the data as it is. Okay. So this one is the memory, what we have discussed in today's class. So in the next class, we deal with what are inputs and what are outputs. Okay, so it is that concept in the next class.